Hello, everyone. Welcome to another webinar from our Rocky Action webinar series. My name is Lucila Almeida, and I'm part of the Rocky DEM support team. Today, we'll talk about coaters, showing how we can use Rocky DEM simulation to improve these equipment and assess operating conditions. Although we'll focus specifically on a tablet coater today, the analysis that will be shown can be extended to other coater types or materials such as food. The coating operation comprises the application of a coating composition to a moving bed of particles with the concurrent use of heated air to evaporate the solvent. The goal of coating, the objective of coating are several. For example, it can be used to mask the bitter taste and unpleasant odor of some drugs, or maybe to improve the appearance for aesthetic or commercial purpose, for example, adding in brand identification, or to prevent drug-induced irritation to a specific site within the gastrointestinal tract. For example, protect the stomach for anti-inflammatory drugs, or maybe control the site of action of drugs. For example, you want to deliver that medication in the colon, so you have to protect it for being delivered in the stomach, for example. It's also used to protect the drug from external environment, for example, air, moisture, or light, in order to improve the stability of the drugs. It also helps make it easier to swallow large drugs, and also to facilitate handling, particularly for high-speed packing filling lines, among other reasons. There are various types of tablet coating equipment. For example, we have the standard coating pen, perforate coating pen, fluidized bed coater. There are also several techniques in order to cover particles. We can name, for example, sugar coating, film coating, and the combination of this working principle, the design, structure, and coating composition, as well as the efficiency of the equipment, determine the choice of which coating equipment should be used. Today we'll model a standard coating pen, as you can see here in this image. It's essentially a circular metal pen that is angularly placed on a stand rotated sport that is rotated by the motor. Heated air is directed to the tablet bed surface that is inside the pen, and the air is exhausted through ducts. The coating solution, as you can see here, is sprayed to the tablet surface by using this spray hand. Non-uniform coating may happen to several reasons. Among them, we can cite inefficient mixing, poor spray design. For example, if you are using a high coating flow rate or an incompatible spray pattern, you can get non-uniform coating across all the tablets. And it can also happen due to non-adequate drying process. The goal here today is to illustrate how Rocky can be used, how can it be very helpful to analyze the spray design and mixing efficient combination. So the goal is to show how to set up this simulation and some of the key post-processing that can be performed. So in this demonstration, you learn how to, first of all, use a custom tablet shape. We are not using sphere, we are using the real tablet shape. We will also use a custom polyhedral as an envelope to check the residence time inside the spray region, and also how to get the coefficients of variability of this coating, the coated mass. I'll also show you how to collect inter and interparticle collision statistics in order to get the distribution of the impact velocity between tablets, and also the collision friction, because that may be a problem depending on the material you're handling. The collision may lead to tablet breakage, and you might want to avoid it. So let's see how Rock can help you do this. And finally, we'll talk about a script that is available that is quite useful for this kind of application as well. So let's see how to set up this problem. This is Rocky interface, and here I'm going to show you the geometry that is used as the coating pen. As you can see, it's a cylindrical pen. Let me make it transparent. So you can see it has 4 blades that help lifting particles. So if you want to see this, set up this problem step by step, please check workshop 9. It guides you step by step through this process. I will not be able to cover everything, so I'll just highlight the important things. First, you can see that the gravity is pointing downwards here, and I'll keep the standard models for collisions, except that here I'm using a numerical softening factor to make simulation run faster. An important point here is that I'm turning on 2 embedded models that are available in Rocky. I will turn on the interparticle collision statistic and also the intraparticle collision statistic. Later on, we'll see what they show us, what kind of information they give us, but it's important that they should be turned on before running the simulation. So I'm asking Rocky to gather the normal impact velocity during tablet collisions, and also the frequency and intensity of the collision impacts. So again, they need to be turned on before running the simulation because I need to store this data. You can see my pen so far is stationary. I want to make it rotate. So here I'm creating a motion frame. I will just name it rotation. And I will create one motion that is a rotational motion. So I will change from translation to rotation. And I want this motion to start at 1 second. So I'll let particle settle down. And I want it to rotate around the z-axis. So I will give a custom constant velocity around the z-axis with 12 revolutions per minute. So this is the velocity at which I want to rotate this pen. And if I go to the motion frame and preview it, you can see there is a frame that is rotating, but so far the equipment is not rotating because I have not assigned this motion frame to the equipment. So that's what I'm gonna do now. If I go back to the geometry, I will assign the motion frame to this geometry. And now if I let's make it transparent. If I move in time, you can see that my equipment is rotating around the z-axis. Let's get back to the view and let's follow the standard step you need to perform when setting up your simulation. In this case, we have 2 materials. We have the material for the particles, and we have the material for the boundary. And essentially, we need to give the density and Young's modulus for the 2 material. And we also need to give the interaction parameters. And essentially, we have 2 important interactions. We have the friction coefficient, both the static and dynamic friction, and also the restitution coefficient. This will be used when computing the particle trajectories. And as you can see here, I've assigned values to both the friction and restitution coefficient between the particle-particle and the particle boundary pairs. Given that I know how they interact, I will now create the particle. I will create a new particle. It always starts with sphere. I don't want a sphere. I want to have my custom particle shape. So I will select custom polyhedral and import my STL of my tablet. I will not scale it now. And if I press here view, you can see my tablet shape. That's the particle we want to model, but it was imported using a sieve size of 0.1 meter. That's not a want. I want to use the original size scale. I mean, I want to use the same size I have in my STL file. So that's an option. You can just keep the size as you have there and run the simulation, or you can use another size, another way of giving size, for example, giving the equivalent diameter or sieve size. In this case, I want to use the original size scale, and here you can see the dimensions of my particle. One important thing is that as we want to collect contact information around the particle, I want to get information at each triangle of my particle. It's important to have a uniform mesh for this particle. In this case, we did this in outside CAD software, and you can see that it's pretty uniform. There is no deformed triangle or large concentration of triangles anywhere, and the particle is well represented using these triangles. So please keep in mind to look for this. Now we need to tell the software where the particles will start, and we have an option to create a volume fill. Essentially, it will place particles. In this case, the only particle type I have. So I want to place 2.7 kilograms of particles inside my coater, and the seed point will be this one, and I want Rock to use my geometry to compute the boundaries. So what I'm telling Rock here is please place particles inside this domain, so you cannot place particle outside my coater, and start from that point. So Rock will keep injecting particles in forming a sphere around that seed point till it fills my drum in this case. We'll also turn on contacts because I want to get stress data. So I need to turn on this collect contact data to have the information in my hand, but only turn this on when necessary because that increases the size of your files. And you can see here I'll have around 5,000 particles in this small simulation. I want it to run for 6 seconds. And I want to run, in this case, I'll run with CPU, but if you have a GPU, just select here how you want to solve the equations. And then I'll press start, my simulation will start. And initially, Rock gives a summary that contains some useful information, for example, number of particles, the time step. I will always check this summary to see if there is something wrong. So if you see weird time step or the number of particles being too high, do not start the simulation. So this is the setup step, and then the simulation will run. Let's now see how to post-process this spray. In this case, we want to check the resonance time inside that spray area. And for this, we have an STL, as you can see there in blue, that you will want to use as a process to restrict the domain in which you want to get the particles residence time. So let's see how to do this. So as you can see, this is the beginning of the simulation. Particles were injected with 0 velocity using volume fill. As soon as I start to move in time, you can see that particles settle down, and then my drum starts to rotate. You can see the velocity of the particle change. And let's now import this process. So if you go to particle, I will create a process that is a polyhedron. And I will import the spray cone, STL. As you can see here, it's placed there. I can change its center and also the scale. So I have it exactly the way the spray cone is in my equipment. I know it beforehand. And what I'm doing here is that I'm collecting information of the particles that are inside that polyhedron only. So at any time, I will know the particles inside that polyhedron. I will do this again because I want to have 2 spray cones. So I'll just do the same steps again. Import a new cone, place it, just like I did. So I want to have 2 spray cones because that's how my equipment works. I'm just placing it. And now, as you can see, we have 2 red areas. And if I go to particle, I can now create a calculation of residence time inside polyhedral 1. And if I go to particles, you can see that I have 2 new properties that are the residence time inside polyhedral 1 and the residence time inside polyhedral 2. And I can show here at the screen that at that time, 3 seconds, that was the residence time each particle spent inside polyhedral 1, the cone 1. But that's not a 1. I want to have the total residence time in both spray areas. So I will select these 2 quantities and create a new custom property that is the residence time inside polyhedral 1 plus the residence time inside polyhedral 2. And now you can see I have a new property that I can show in the 3D view. And you'll see that every particle will have a certain value of the residence time inside the spray area. If I move, you can see that as I move in time, the residence time changes for each particle. And the goal here is to now work with this residence time information in order to get what we call the coefficient of variability. So, as you can see here, the coefficient of variability is defined as the ratio between the standard deviation over the average of the coating mass. And the goal here is to get this ratio, because with this ratio we know how uniform is the coating of the particles. So let's see how it goes. So again, we have the residence time of particles inside that. I can come to Rocky and get a time plot and plot here the total residence time and ask for the average and the standard variation of this coating mass. And you can see that in this plot you have both. We can just place them at the same axis. So you can see that we have an average and we have the standard deviation, and we can create a new formula, a new equation that gives us the coefficient of variance that is given by this ratio. And now we can see in the plot how it changes with time. So you can see that the variation decreases with time, and we can also change the axis scale, making it logarithmic, because that's how most people use this information. Given we have now a steady state, we can extrapolate this data and check when we would reach the target value. And that's what I did here. I got that plot and I have extrapolated data from the range I had. And you can see that after a certain time, I would reach the limit that is my target. It would take 0.14 hours to get the limit of 6.25 of the coefficient of variability. Moving on to the interparticle collision statistics, again, the goal here is to check the impact velocity between particles. So remember, we have turned on interparticle collision statistics. And now you can see that I have several new properties. One of them is the average. So you can see that's the average velocity between all the collisions that happened for each particle during that output. And you can, for example, check the histogram showing this velocity distribution. So you can check if it happens to have collisions with high impact velocity in your equipment. We can also check the intraparticle collision statistics. This time I don't want to get information of collision between particles. I want to see for the particle itself, how is the distribution of the collision. So I can go to particle and show, for example, the frequency of collision. I can also get time average. So now what I'm doing here is I'm getting from time 40 to time 60. What is the distribution of the collisions in a tablet? So for all the tablets, I'll check where the collisions happen in each tablet, and I will show this in a representative particle. So getting the average, I can now show here in a particle, in a 3D view. You can see that most of the collisions happen at the edge. I'm just making the edge white. And let me show you the frequency. As I was telling you, most of the collisions happen at the edge of the tablet, and that may be an issue depending on the velocity you may chip your particle. That was the end of this presentation, but I encourage you to take a look at workshop 9 in our portal, because that shows another way of computing this spray region. We got information of the spray distribution using the residence time inside that cone as the key parameter. But that's not necessarily true, because particles that are above the surface of other particles, they do not receive the liquid coating. So what this macro does, what this script does, is that it computes the amount of mass received by each particle based on a camera. So facing the particles that are facing the camera that way, as you can see here, they will receive a certain amount of liquid coating that is proportional to the exposure of that particle to the camera view. And we can work with this value just like we did. Instead of having the residence time, we have this cumulative visibility per tablet, and we can also get the coefficient of variability and also the distribution of this visibility above the triangle surface, above the particle surface. So you can see if it may happen that one surface of the particles is not equally coated as other surface of the particles. So this script is very cool because it allows you to check the visibility based on the exposure of that triangle surface to the camera, and also get the distribution of this visibility over the surface of the tablet.